Here we have an electric dipole with a plus q and minus q separated by a distance d. The first thing we're going to do is find the electric potential field. That is the amount of work it takes to move 1 coulomb of charge from infinity to some position r. We can use superposition to find the potential at point P due to the plus Q and then due to the minus Q and just add them. Here is the potential at point P due to charge Q, and here is the potential at point P due to charge minus Q. Rewriting our potential field in this form, we see that the potential is 0 if you're equal distance from the plus Q and minus Q charge. So the XY plane has a potential of 0, so it takes no work to bring that 1 coulomb of charge from infinity in if you're on the XY plane. And that makes sense because you're always equal distance from the repulsion of the plus Q and the attraction of the minus Q. So there's no net force. Let's look at the approximation we can make if the point we're finding the potential at is much greater than the separation between the charges. So if we zoom in this region, we have the bottom figure here. When we zoom in, R1R and R2 look like they're parallel. This dashed line starting at Q that goes down to R2 is perpendicular to R2. We have a right triangle here where the hypotenuse is D, and this side here is the difference in length of R2 and R1. And so this side is the hypotenuse D times the cosine of this angle theta, which is just the theta coordinate of point P. For R2 minus R1, we can substitute D cosine of theta. Approximating R1 and R2 as R, we have R squared in the denominator. Here is our exact potential for our electric dipole, and here is the approximation for the potential when the distance from the dipole is much greater than D. Now that we have the scalar potential field, we can take minus the gradient of it to get our electric field intensity for the case when R is much greater than D. Here is the expression for minus the gradient of the potential in spherical coordinates. Applying this to our potential field, we get the following. For the electric field intensity, when the distance from the dipole is much greater than the separation between the charges in the dipole.